In medium voltage systems, such as a 4160/2400 volt system, it's normal to have some ground current. This occurs because of the inherent capacitance between energized conductors and the ground. However, this current should be minimal, usually less than 1 amp. If you're experiencing higher ground current, there could be several reasons. When examining a pothead, firstly, loose connections on the pothead or buswork could be the issue. Secondly, contaminated insulation may be to blame. Thirdly, moisture inside the pothead can lead to increased ground current. For a substation ground, firstly, faulty equipment like transformers or switchgear could be the cause. Secondly, damaged underground cables or splices may be contributing. Thirdly, high soil resistivity or excessive moisture in the ground can also increase ground current. Fourthly, improper grounding design or installation is another potential factor. To troubleshoot a pothead experiencing high ground current, firstly, tighten all connections and inspect for any signs of damage. Secondly, test the insulation of the pothead using a megameter. Thirdly, check for moisture accumulation and remove it if present. When addressing high ground current in a substation ground, firstly, inspect all equipment for signs of damage or leaks. Secondly, perform continuity tests on all grounding conductors and connections. Thirdly, measure the ground resistance using a ground resistance tester. Fourthly, consider soil resistivity testing to determine the effectiveness of the grounding system. Several resources can provide further guidance. IEEE Standard 80.1986 Guide for Safety in AC Substation Grounding is a valuable resource. Another useful document is the Power Engineer's Guide to Electric Power Substation Grounding, also known as IEEE 1050. Additionally, you can find information on grounding in electrical power systems from various sources. Remember that ground current in medium voltage systems, while normal to some extent, should be kept to a minimum. High ground current indicates a problem that needs to be identified and corrected to ensure safety and proper system operation. Always follow safety procedures when working with medium voltage systems. When investigating a pothead issue, focus on connections, insulation, and moisture. For substation grounds, consider equipment health, cable integrity, soil conditions, and grounding design. By systematically checking these areas, you can effectively troubleshoot and resolve high ground current problems. When checking connections, ensure they are clean and tight. Loose connections can create resistance, leading to heat and increased current leakage to ground. Insulation testing will reveal any degradation or damage to the pothead's insulation. Low insulation resistance indicates a pathway for current to flow to ground. Moisture can significantly reduce insulation resistance. If moisture is present, dry out the pothead and address the source of the moisture intrusion. In the substation, carefully inspect all equipment for signs of overheating, corrosion, or physical damage. Look for all leaks from transformers, which can indicate insulation breakdown. Underground cables and splices are vulnerable to damage from moisture, soil chemicals, and physical stress. Damaged cables can leak current into the ground. High soil resistivity makes it difficult for ground current to dissipate, leading to higher ground potential. Excessive moisture in the soil can also increase ground current by providing a conductive path. Ensure that the grounding system is properly designed and installed according to applicable standards and codes. Improper grounding can create high ground potential and increase the risk of electric shock. When measuring ground resistance, compare the results to the design specifications. High ground resistance indicates a problem with the grounding system. Soil resistivity testing involves measuring the resistance of the soil at different depths and locations. This information is used to determine the optimal grounding system design. Keep in mind that ground current can also be affected by nearby electrical systems. Ground faults in neighboring facilities can sometimes contribute to ground current in your system. Consider the possibility of external sources of ground current when troubleshooting. In some cases, harmonic currents can also contribute to ground current. Harmonic currents are caused by nonlinear loads, such as electronic equipment and variable speed drives. If harmonic currents are suspected, use a power quality analyzer to measure the harmonic content of the current. Mitigating harmonic currents may require the use of filters or other specialized equipment. It's important to understand the specific grounding configuration of the medium voltage system you are working with. Common grounding configurations include solid grounding, resistance grounding, and reactance grounding. Each configuration has its own characteristics and advantages. Solidly grounded systems provide a low impedance path for ground fault current, resulting in rapid fault clearing. However, they can also experience high fault currents, which can damage equipment. Resistance grounded systems limit the ground fault current to a predetermined level, reducing the risk of equipment damage. Reactance grounded systems use a reactor to limit the ground fault current. Choice of grounding configuration depends on the specific application and the desired level of protection. Always consult with a qualified electrical engineer to determine the appropriate grounding configuration for your system. Grounding is a critical aspect of electrical safety. A properly designed and installed grounding system helps to protect people and equipment from electric shock and damage. Regular inspection and maintenance of the grounding system is essential to ensure its continued effectiveness. This includes visual inspection of grounding conductors and connections, as well as periodic testing of ground resistance. Any signs of corrosion, damage, or loose connection should be addressed promptly. It is also important to keep accurate records of all grounding system inspections, tests, and maintenance activities. These records can be helpful in identifying trends and preventing future problems. In addition to following applicable standards and codes, it is also important to follow best practices for grounding. This includes using high-quality grounding materials, ensuring proper installation techniques, and providing adequate protection against corrosion. It is also important to educate personnel about the importance of grounding and the proper procedures for working with grounded systems. Proper training can help to prevent accidents and ensure the safety of workers. If you are not familiar with grounding systems over 1 kV, it is important to seek guidance from a qualified electrical engineer or other expert. Grounding systems can be complex and require specialized knowledge and skills. Do not attempt to troubleshoot or modify a grounding system without proper training and experience. Always follow all applicable safety procedures when working with electrical systems. This includes wearing appropriate personal protective equipment, such as gloves, eye protection, and arc flash protection. Be aware of the potential hazards of working with electricity and take steps to minimize the risks. If you are unsure about any aspect of working with electrical systems, consult with a qualified expert. Remember that safety is always the top priority. By following these guidelines, you can safely and effectively troubleshoot high ground current problems in medium voltage systems. Keep safety in mind at all times when working with electrical equipment. In addition to the resources mentioned earlier, there are many other sources of information on grounding available online and in print. These resources can provide additional guidance on grounding principles, design, installation, and maintenance. Take advantage of these resources to expand your knowledge and improve your understanding of grounding. Grounding is a constantly evolving field, so it is important to stay up to date on the latest developments and best practices. Attend conferences, read industry publications, and participate in online forums to learn from other experts in the field. By continuously learning and improving your skills, you can become a valuable asset in the field of electrical engineering. Remember that grounding is not just a technical issue, it is also a legal and ethical responsibility. As an electrical professional, you have a duty to ensure the safety of people and equipment. By following best practices for grounding, you can help to prevent accidents and protect lives. Grounding is an essential part of any electrical system. By understanding the principles of grounding and following best practices, you can ensure the safety and reliability of your electrical systems. Always prioritize safety when working with electrical equipment and seek guidance from qualified experts when needed. Grounding systems are designed to provide a low impedance path for fault current to return to the source. This allows protective devices such as circuit breakers and fuses to quickly interrupt the fault and prevent damage to equipment and injury to personnel. A properly grounded system also helps to reduce the risk of voltage transients and other power quality problems. Voltage transients are sudden, short-duration increases in voltage that can damage sensitive electronic equipment. Grounding can help to dissipate these transients and protect equipment from damage. Power quality problems can also be caused by harmonic currents. Grounding can help to minimize the effects of harmonic currents and improve the overall power quality of the system. A well-designed grounding system is an investment in the safety and reliability of your electrical system. The cost of a properly grounded system is typically small compared to the potential costs of accidents, equipment damage, and downtime. Make sure that your grounding system is properly designed, installed, and maintained to ensure its continued effectiveness. Grounding is a critical aspect of electrical safety and should not be overlooked. By understanding the principles of grounding and following best practices, you can help to protect people and equipment from electrical hazards. Always prioritize safety and seek guidance from qualified experts when needed. Continuous learning and improvement are essential for all electrical professionals. Stay up to date on the latest developments in grounding technology and best practices to ensure that you are providing the best possible service to your clients and customers. Grounding is a vital part of electrical engineering and plays a critical role in ensuring the safety and reliability of electrical systems. Grounding involves connecting non-current carrying metal parts of electrical equipment to the earth. This provides a low resistance path for fault current to flow back to the source, allowing protective devices to quickly trip and clear the fault. A properly designed and installed grounding system protects personnel from electric shock hazards and prevents damage to equipment. There are several types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. The type of grounding system used depends on the voltage level, the size of the electrical system, and the specific application. Solidly grounded systems are commonly used in low voltage systems, while resistance and impedance grounded systems are typically used in medium and high voltage systems. Resistance grounding limits the fault current to a safe level, reducing the risk of damage to equipment. Impedance grounding uses a reactor or a resistor to limit the fault current and provide additional protection. The selection of the appropriate grounding system requires careful consideration of several factors, including safety, reliability, and cost. A qualified electrical engineer should be consulted to determine the best grounding system for a particular application. In addition to the grounding system itself, it is also important to ensure that all grounding conductors and connections are properly sized and installed. Grounding conductors must be large enough to carry the maximum fault current without overheating or melting. Grounding connections must be tight and corrosion resistant to ensure a low resistance path for fault current. Regular inspection and maintenance of the grounding system is essential to ensure its continued effectiveness. Grounding conductors and connections should be visually inspected for signs of damage or corrosion. Ground resistance should be measured periodically to ensure that it is within acceptable limits. Any problems with the grounding system should be corrected promptly by a qualified electrician. Grounding is a critical aspect of electrical safety and should not be overlooked. A properly designed and installed grounding system protects personnel from electric shock hazards and prevents damage to equipment. Regular inspection and maintenance of the grounding system is essential to ensure its continued effectiveness. Always consult with a qualified electrical engineer or electrician for any questions or concerns about grounding. Grounding systems are designed to provide a safe path for fault current to flow back to the source. This allows protective devices to quickly trip and clear the fault, preventing damage to equipment and injury to personnel. A properly grounded system also helps to reduce the risk of voltage transients and other power quality problems. Grounding is a complex topic with many different aspects. It is important to have a thorough understanding of grounding principles and best practices to ensure the safety and reliability of electrical systems. There are many resources available to help you learn more about grounding, including books, articles, websites, and training courses. Take advantage of these resources to expand your knowledge and improve your skills. Grounding is an essential part of electrical engineering and plays a critical role in ensuring the safety and reliability of electrical systems. By following best practices for grounding, you can help to protect people and equipment from electrical hazards. Grounding is a critical aspect of electrical safety, and it is essential to understand its principles and applications.